This is exercise 7 from section 1.1 of the text. I want to prove that the square of an integer is either of the form 3k or 3k plus 1 for some integer k. Now, one thing to note is that this is a proof. And so what we want to do is to provide a formal and logic-based argument that shows that the square of an integer is either the form 3k or 3k plus 1. So I'm going to write this up a bit differently than I would an example that only asked me to show, that the statement was true. So here in this proof, I want to start with an integer. The whole idea is to prove that the square of an integer is of a certain form, so let's just start with that integer itself. So let's let some integer a be given. Once again, this z here represents the set of all integers. And now I want to use the division algorithm to show that this hint is actually true. So the division algorithm says that if I divide a by 3, I get the following result. So let's say division algorithm with b equaling to 3 gives the following. So I'm dividing a by 3, and I get the following result. I get that a is equal to 3 times q plus r with 0 less than or equal to r strictly less than 3. So once again, the division algorithm guarantees that if I divide a by 3, namely that there exists a unique q and r so that this inequality with the remainder holds. And so what is this actually saying? It says that since 0 is less than or equal to r strictly less than 3, we have 3 options for r. Namely, we can have that r equals 0, 1, or 2. So a has to be of the form 3q if r is equal to 0, 3q plus 1 if r is equal to 1, or 3q plus 2 if r is equal to 2. And so this is why this hint is true. And so how do we use it to help us? This actually tells us that we can break this problem down into 3 cases. We want to show that the square of an integer is of the form 3k or 3k plus 1. So if we only have 3 options for the form that integer has to be, we can square each of these options and see if we get the result. So let's start with case 1. That's going to be namely that a is of the form 3q. So what happens when we square it? Well, we get that a squared equals 3q squared, and then that's going to give us 9q squared. And I want to show this is of the form 3k or 3k plus 1. Well, if I factor out a 3, I'm going to get 3q squared left over, and I can just let this 3q squared be equal to k. And so indeed, in this case, a squared is of the form 3k. Let's look at the next case. Here we have that a is equal to 3q plus 1. So we have a squared is going to be equal to 3q plus 1 squared. And if we distribute that, we're going to get 9q squared, 9q squared plus 6q plus 1. And so let's try to factor out, we can't factor out a 3 from each term, but we can factor out a 3 from the first 2 terms. That will give us 3 times 3q squared plus 2q, and then we'll have this plus 1 left. And once again, if we let 3q squared plus 2q equal k, then we see that a squared is of the form 3k plus 1 as desired. Next, let's look at the next case. 3q plus 2 is the form that a is in here. And if we square it, we get a squared equals 3q plus 2 squared. And so if we distribute, we get 9q squared plus 12q plus 4. Again, we cannot take out a three evenly from each term, but we can write this in the following way. So let's say we've got 9q squared plus 12q. Clearly we can take a 3 out of both of those terms, but what about this 4? Well, if I rewrite the 4 as 3 plus 1, then I can take a 3 out of each of the first 3 terms and just have this 1 left over. So that's going to give me 3 times 3q squared plus 4q plus 1, and then all of that plus 1. And so here, once again, I'm going to let this term in the parentheses just be k, and k is an integer because each term in here is an integer. And we see that a is of the form 3k plus 1. And so it follows, and this is the conclusion statement, it follows from the above cases that the square of an integer is either of the form 3k or 3k plus 1. And I'm going to put this square here. That means that the proof is finished.